Hello everyone. This is one of a series of videos that I've dedicated to chapter 11 of Killers and Boosters. And as a reminder, you have a scanned copy of this chapter available on Blackboard. In previous videos, I've looked at reducing agents, I've looked at reactions of aldehydes and ketones with nitrogen-containing functional groups. And on this video, I'm going to be looking at acid derivatives, and specifically the hydrolysis of acid derivatives. You have here an example of the hydrolysis of various level 3 functional groups. And as you can see, many level 3 functional groups will hydrolyze to carboxylic acid, some more easily than others. And it is the conditions that tell you how easy that hydrolysis happens. So for example, here an ester, you need relatively strong conditions, 100 degrees, while for example an acid anhydride hydrolyzes at room temperature. In some cases, the reaction can happen simply in water, and in others, as you can see from the examples, you might need an acid or a base to facilitate the reaction. In some cases, for example, here the example of the nitrile, it is possible, playing with the conditions, to isolate the intermediate hydrolysis species. So for example, instead of reaching the final hydrolysis product, which would be the carboxylic acid, it is possible with slightly milder conditions to isolate an intermediate hydrolysis stage, which is the amide. So I'm going to ask you to stop the video right now and have a go at proposing a mechanism for the alkaline hydrolysis of ethyl ethanoate. So how would you make ethanoic acid, acetic acid, by starting with ethyl ethanoate, which is this compound here, and in the presence of a base. So please stop the video now. Hopefully you stop the video as I asked you to and had a go at proposing a mechanism for this hydrolysis. A couple of things I need to keep in mind before proposing a mechanism. One is, the most important one, is that because I'm in a basic medium, I am not going to have hydrogen ions. So I cannot have these hydrogen ions to play with in my mechanism. What I can have, if necessary, is molecules of water. So I've got molecules of water, and I also have OH minus hydroxyl ions if necessary. So then, as with many cases, or in most cases with a carbonyl group, the first step is an attack of this carbon with this partial positive charge by the nucleophile, in this case the OH, and the breaking, a temporary breaking of the double bond in the carbonyl group. And if I draw the molecule, I still have this general structure that hasn't changed. I've gained an OH, a hydroxyl group that has just entered the molecule. I've got my oxygen with a negative charge. Because I am in basic medium, that oxygen with a negative charge is stable. It is not protonated. And then the next step is reforming the carbonyl group. And of the two fragments that could leave the molecule, this one, well, will send us back to square one. And apart from that, it's not a great leaving group. The hydroxyl ion is not a particularly good leaving group. Or I have this one, and this one is a better leaving group. So the next step would be the reforming of the double bond between the carbon and the oxygen, and this section of the molecule leaving. So you would end up, or we would end up, with again the carbonyl group reform, but in the form of a carboxylic acid, and the fragment, an ethanol with a negative charge, having left the molecule. And that would be the final reaction. So now I'm going to ask you again to stop the video and propose a mechanism for the acid hydrolysis of ethyl ethanoate. And in this case, you need to remember, because you are in acid medium, you are not going to have oxygens with a negative charges. They will be always protonated, and you can have hydrogen ions because you are in acidic medium and you actually do have them. And you can use as you prefer hydrogen ions with this notation, H plus notation, or if you are more comfortable, you can make the mechanism with writing your hydrogen ions as H3O plus. So please stop the video now and try to propose a mechanism for this reaction. Hopefully you stopped the recording and had a go at proposing a mechanism for the acid hydrolysis of ethyl ethanoate. Now I need to think carefully what's going to be my nucleophile in this case. In this case, in the previous case when we were looking at the basic hydrolysis, the nucleophile was the hydroxyl ion, OH-. In this case, my nucleophile is going to be a molecule of water. It cannot be the hydrogen ions, that oxygen is protonated, it's not a nucleophile, but molecules of water can be my nucleophiles, will be my nucleophiles. And what is the problem? Well, that water is not a great nucleophile. Hydroxyl has a negative charge, it's a better nucleophile than a neutral compound like water. So I need to improve a bit the partial positive charge of my carbonyl bond. I need to make it a stronger partial positive charge if I want to make it more attractive to a nucleophilic attack. So what I can do, a sensible way of doing this would be by protonating the oxygen of the carbonyl group, and just to put some strain in that carbon double bond oxygen to make the oxygen pull more charge from the carbon and increase that partial positive charge. So this is the first step, the protonation of the carbonyl group, of the oxygen of the carbonyl group, and oxygen, and then I have a better partial positive charge on that carbon. So now if I have a molecule of water that can act as a nucleophile much more easily. So I attack the carbonyl group, those electrons bounce, and I end up with this intermediate step in which you have a molecule of water that has become, that's part of the molecule, but at the moment, because the oxygen hasn't lost the two hydrogens, is protonated. I've got a hydroxyl group here, and I've got the oxygen and the ethyl group on this side of the molecule. Quite easily, let's say with another molecule of water, we can remove that extra hydrogen that we don't want to come up with this compound in which I have two hydroxyl groups in the structure. And again, I still have that section of the molecule. Now I need to reform the double bond of the carbon-oxygen double bond. And I'm going to need to make this leave the molecule, this fragment of the molecule, to form a carboxylic acid. And because we are in acidic medium, it's not going to be able to come out as an oxygen with a negative charge. That oxygen wouldn't be protonated in acidic medium. So as it stands in this medium, it is not a good leaving group. So the next step, what I have to do is to protonate that oxygen again by capturing a hydrogen ion. I'm able to protonate this oxygen, and form, again, we haven't lost anything yet. We've got the two hydroxyl groups and this oxygen that has become protonated. And that is a good functional, a good leaving group in acidic medium. So the next step is for one of the oxygens, whichever it is, to form a double bond with the carbon. This means that this fragment of the molecule can leave, the alcohol leaves the molecule, and the final, and you will need to lose a hydrogen of this hydrogen to not have a carbonyl group protonated. So by simply removing a hydrogen ion from the OH and the alcohol group, you would end up forming the carboxylic acid, and you would have, well, the alcohol part form too that has left the molecule, and this would be the final product. Following a similar mechanism to the one I wrote before, I'm going to ask you to stop the video now and have a go at proposing a mechanism and the final products of this particular reaction. And you have the answer on page 372 of Killer and Wuthers. So you can check your products with the book. Nitrates. I'm going to ask you again to stop the video and propose a mechanism for the hydrolysis of a nitrile in acidic medium, an acid hydrolysis. So please stop the video and try to come up with a mechanism. And as a reminder, your nucleophile is going to be the molecule of water. And you cannot have negative species in the medium. You cannot have nitrogen with negative charges, or even an oxygen with negative charges. They would always be protonated because you are in acidic medium. So keep that in mind when you are working through the mechanism. Hopefully you stop the video and have a try at proposing a mechanism for this acid hydrolysis of a nitrile. So if you look at it, we have, again, the carbon with the partial positive charge is going to be this one. But remember that the nucleophile we have here is water. And as in the previous case of an acid hydrolysis of an ester, water is not a great nucleophile. So you need to do something to improve the partial positive charge of that carbon. You need to make it more attractive, a stronger partial positive charge. And the way to do that is by protonating this nitrogen. As in the previous case, we protonated the oxygen of the carbonyl group. Well, in this case, we are protonating a nitrogen by using a molecule of water. And now, because this nitrogen suddenly has a positive charge, that has increased the partial positive charge of that carbon. That nitrogen is pulling more strongly of the electrons from the bond and making it more attractive to nucleophiles. And then a molecule of water can attack that carbon, and you form this intermediate species that here is called B. And then simply by losing a hydrogen here, because to make this into a hydroxyl group, and protonating this nitrogen, because again you need a subsequent attack. Remember, you are aiming for this carboxylic acid group, so the carbon double bond nitrogen is not enough. There are more steps to it. But again, you are improving the partial positive charge of this carbon by protonating the nitrogen. The nitrogen pulls more strongly of the electrons from the bond that has with the carbon and makes that carbon more attractive to nucleophiles. So then you have another molecule of water that attacks the carbon with the partial positive charge, and you form this intermediate species D that has a hydroxyl. It has a molecule of water that can easily lose a hydrogen and become another hydroxyl and an amino group. The next step is something has to come out of that structure, because you want to reform the carbon double bond oxygen. And again, NH2, you cannot liberate an NH2 minus. It's not stable in acidic medium. It would be protonated. It would be in the form of, it would gain a hydrogen. And also, it's not a particularly good functional group. A neutral molecule, it's not a particularly good leaving group. A neutral molecule is always a better leaving group. So the next step to make compound E is protonating that nitrogen to make it into an ammonia molecule that can leave the structure more easily. Then it's just a question of losing this hydrogen and you form the carboxylic acid. Depending on the conditions, it is possible to stop at the amide stage, in that intermediate stage in which the carbon double bond nitrogen is formed, and that is because you have these tautomeric forms between the carbon double bond nitrogen and carbon double bond oxygen, and with the nitrogen single bond. And typically you require milder conditions to form this amide, and then if you continue the hydrolysis, maybe increasing the temperature and leaving it for longer, you form the carboxylic acid. And in the previous slide I gave you this example, this nitrile, in which with milder conditions, shorter time and lower temperature, you form an amide, and then increasing the temperature and leaving it for longer, 6 hours instead of 1, you form the corresponding carboxylic acid. And thank you for watching, and this is the end of this part of the video, and I hope it was useful.